I'm sorry, can you unmute yourself on the computer? Uh, on the Zoom account, you still muted despite the microphone.
Okay, can you hear me?
Yes.
Yeah. Yeah. Okay, good. Thank you.
Online too.
Yeah, yeah. Thanks for coming, everyone. Okay.
Ça va bien, Joanne va bien.
Okay. Everybody pretty much here. Let's see. Well, we're missing one maybe. But
Well, the guy who doesn't come up with it.
oh, he doesn't come on. Oh, okay. All right.
Get stuff.
Okay, so we can start. We have a problem? Okay.
Can you speak?
Yes. I was muted before, and they told me, and I unmuted. Yeah, that what was. Okay, great. Thank you. Okay, so we all have audio, right? Okay, all right. Yeah, right. Okay. So first thing I'm going to repair. Yeah, I got stuck at some point, a silly point. I can repair that for you quickly, but so as not to waste time, I remind you where we were. So we established the basic decay estimate, linear decay from H4 to L2. This is the first one written above. We established a nonlinear damping estimate, this energy estimate, that gives us slaving of the H5 norm to the L2 norm. And okay, and this is, so they both involve exponential decay. Two different, I need to make them two different rates. Before I had them at the same rate, that caused a problem. This is actually timely because we're going to do, this arises constantly when you do invariant manifold theory for ODE, which is what we do next. So this is good practice to see where I went wrong and what I need. Basically, the idea is very simple. It's that, okay, this is like a memory kernel here, exponentially decaying memory kernel that's sort of making everything count only near T. So it's kind of like the decay rate for H5 will be the decay rate of L2. But that's only true if the L2 norm decays more slowly than the memory kernel. If we put them at the same rate, they kind of resonate. They gave us an extra factor of T, which is no good, and we'll see here. So, but of course, we're free to play with both of these. This is not a zero, but a theta. I need to take the memory kernel decaying faster than the decay rate that I want to achieve. And I can do that just by giving up some of the decay that I have. And I don't use it. Okay, as always, we defined alpha of t to be the weighted exponential norm in H5, and we want to show that's bounded and small compared to the data, and then we're done. Okay, and what we specifically we wanted to prove, we wanted the damping estimate. Sorry, the bootstrap. We want to show that alpha of t is less than or equal to v not H5 with a constant plus alpha of t squared. That's this bootstrap. Okay. But so we started and we correctly showed an L2 bound using just variation of constants and the linear decay. We arrived at this bound we found that the L2 norm is bounded by an exponentially decaying term at the slow rate theta times exactly what we want. The initial data plus alpha squared. Then I attempted to do 2, which is, okay, 2 is, so we've got, okay, we took care of L2. Now we're going to do an inner bootstrap. We're going to improve that to a bound on H5. To do that, we use our nonlinear damping, which is NLD, is written above. So NLD was here, all of this, and I'm going to now freely substitute in there. So I'll take tau between 0 and t, and I want to estimate the H5 norm of tau squared. Okay, so the first term is clear. I'm just copying the first term of the nonlinear damping estimate. The second term, I'm doing some things. I'm using that. I'm using the L2 bound, which is written here. I'm substituting that in. And then, what else am I doing? I'm pulling out the I'm pulling out the decay in t altogether. I'm pulling this term out in front. That's okay. That's here. What have I done? I think I pulled out too much, didn't I? It's just t minus tau, so it's just minus 2 theta. Theta tilde. Oh, no, I did. Okay, I pulled out in front of, okay, no, that's fine. This is what I want. T, it's the same as this. These are the same. And what's left is the tau. Okay, I have a positive 2 theta tau, but I have a negative 2 theta, sorry, a positive 2 theta tilde tau, a negative 2 theta tau. So putting them together, I have this. It's not a good term. It's exponentially growing because I assumed this was positive, right? But it's okay. The main thing is that it should not be 0. If it were 0, I integrate, I get a factor of tau. This is the only bad thing that can happen, which I managed to achieve.
Integrate up to tau or up to t?
From 0 up to tau only. I'm only estimating at tau, but just the way the final estimate is, I want to allow tau to be between t and 0, so I always use alpha of t to control tau. Okay, so I integrate this. So let's see, L2 bound is written, okay, that was for tau, and this should be tau, and this should be t. No, it is t because of, notice, alpha of t includes tau in the soup. Yeah, this is just like strategic to then, yeah, it's annoying. Sorry about that, but that's what we have to do to get the final bound. Yeah, so that's a subtle point, right? That I always use alpha of t for any tau that's less than t. Now I look at this. This is just going to be, it's an exponential, it's growing. The main contribution is at tau, and the rest is 1. So it's just e to the 2 theta tilde minus theta tau times a constant, possibly big. It's of order 1 over this difference, but then times times e to the minus 2 theta tilde. Together, these give, this is like a constant times e to the minus 2 theta tilde. Oh, sorry, that's a tau. And times e to the 2 theta tilde minus theta tau.
They compensate.
They just compensate perfectly. These cancel, and they leave me the e to the minus theta t, which is what I'm after. That's the bound that I had. That's what I'm getting from the linear part. And that's what I used in the definition of alpha. So now when I multiply this estimate by alpha of tau, I want to do one more step. I want to say, and this is less than or equal to C times V naught H5 plus alpha of T squared. Did I write that correctly? Oh, I forgot to put, this is squared because, right, I used the L2 norm to estimate the L2 norm squared. Here it's L2 norm squared. So there was a square there. And I can simply bound it by this and e to the minus theta tau. Good. Okay, and so that 2 theta tau. So that gives me alpha of tau is less than or equal to, e to the theta tau, v tau h5, and that is less than or equal to the square root. Times nothing, because the square root of e to the minus 2 theta tau cancels the e to the theta tau, and this is what we get. This was a squared. So I get just what I wanted. Now I take the supremum over tau. I'm sorry, this is alpha of t. Sorry, alpha of t. I have to take the sup over tau less than or equal to t of this, but it's independent of tau. It's this. And that is what my goal was. So it's hidden. This is now complete. And that was what was missing. We just needed this bootstrap estimate, and then the rest of the argument went as in finite dimensional ODE. And that gave us our first result, which says if we have all spectra with real parts strictly negative, then we can if we get not only linearized decay, but nonlinear decay at essentially the same rate. Okay, so that was, now we're repaired. Any question on this part? Yeah,
To remember what we have assumed, did we have smallness condition or we did not use it?
no, we have to take a smallness. So it's a nonlinear stability for sufficiently small initial data in H5. And then perturbation, sorry, the initial perturbation must be small in H5. And then we get global existence and exponential decay in at the same linear rate. At this rate, we'll have a similar bound for the nonlinear perturbation with twice this constant. But I mean, it could be anything, any constant bigger than that one, arbitrarily close, would work. So now we're up to the level of the basic ODE theorem. We went on. I just borrowed, I've now paid you back, but I took a loan and went on, and we looked at the equivariant stability. So noting that traveling waves, in fact, don't fit this theorem, but have a symmetry of translation, we factored out the symmetry, and we got to this same point. We had decay, and all we needed was actually a nonlinear damping estimate. We did not have that. And once we have that, we do this argument I repeated here on the board. And so let me show you then that nonlinear damping estimate. But first, well, okay. But what's the equation? I'll remind you of the equation. It's dTV equals negative a bar v, negative dx, a bar v minus dx squared, v minus or plus dx n of v. And then there were two new terms, minus delta dot of t, dx v plus dx w bar. This is the standing wave profile. And it's also equal to a right zero eigenfunction R that was mentioned over and over. Okay, so I in the linear, well, even in the nonlinear analysis, I completely factored out this delta. But to do that, I made certain coordinate changes that don't, at the linear level, I projected onto the good subspace of L, but that doesn't go well with an energy estimate. So I need to go back to the full equation, or at least this is the only way I know how to do it. And I do it here. And so now there is a delta dot in here and a derivative of W bar, but it will not hurt, it turns out. But first, I just need to mention something. Okay, so what I want to, I said this earlier, and I want to give more details. So I said left and right eigenfunctions are in H5. How do I know that? Because I have, well, okay, let's see. What do we get from, so eigenvalue equation is L, let's say LR equals 0. Now, this is exactly just from, this is like the Fredholm section, Fredholm theory in Evans' BDE book. It's the same. You use that somewhere. So we assume, as usual, that there is some point in the resolvent set. And that means there is some lambda naught such that lambda naught minus L inverse is bounded from x to d of L. So from L2 to H2. But that, the first step, we just observed that that means if I take LR equals 0 and write it as lambda naught minus LR equals negative lambda naught or equals lambda naught R. And I just used that R is in L2, oh, sorry, in H2, sorry, L2. I get that inverting I find that this is in the domain of L squared, which is, domain of L, which is H2. So I see smoothing of eigenfunctions. So I know they're at least in the domain. How do I get higher? Well, here I actually need, so if F is smooth enough, which is the same as saying A bar is smooth enough. We're at the linear level here. Then I can differentiate the equation. So I get L dx of R is not zero, but lower derivative terms. Terms of order, well, let's see what they are. Dx A bar, dx bar. Okay, and so this is fine. We've already shown that R is in H2, so this is H1. This is just assumed smooth as could be. So we're in we're in L2 for sure. But we've just shown that that we can go from, if the right hand side is L2, we can go to I'm sorry. What am I saying? If dx, right, so if dxr is in H1, then dxr is in H3. So treating now this as, now I have it using smoothing on the differentiated equation. So it's really, it's not, there's no boundary. We can go as high as we like by just successively differentiating the eigenvalue equation, noting that the lower order terms don't affect the smoothing, and we can move up the ladder and get as smooth as we like. What is the only obstacle? If the coefficients lose smoothness at some point, the coefficients of the equation. Okay, so this is pretty familiar, but I didn't say it, and worth noting, especially because we need it right now. So some of the things, and this works for both left and right. You could just look at the dual operator to find the same thing for the left kernel. Okay. So now, so let's just take the, oh yes.
The previous one.
Because dxr, because we already showed R is in H2 with the previous smoothing estimate. Yeah, so now dxr should be in H1. And then
Can you repeat the same argument?
yeah, we repeat the same argument. And
L2 to H2?
yes,
Using the L0 minus L?
yes, yeah.
Does not commute with the zero minus L. Derivative.
It doesn't commute with what?
Derivative does not commute with the zero minus L.
No, but here I'm not commuting. I'm just
So
I'm starting with
then how?
well, I'm going to do see, I have lambda naught minus L dxr is equal to lambda naught dxr. Same, that part is the same, plus order of dxr. So these are basically the same, and they're both actually in H1, which I don't even need that. These are in L2, so this will be in H2, and I've gone up one. Yeah, yeah,
It does not commute.
yeah.
Lower order.
That's the trick. Yeah, I should have gone one step further. It's actually not so. Yeah. Anyway, yeah, I'm glad you asked that. Yeah. Okay, so back. Okay, so we're gonna do. Actually, we do the same thing we did before. So we take dx to the fifth of v squared over 2. We take the time derivative. So this is just a very standard kind of energy estimate, and that will be dx to the fifth v against dx to the fifth dt v. And then we'll go term by term. There's a dt of v up above. So I need to take 5 derivatives and see what I get and take the inner product. But what I do know is there's only one term. There's the highest derivative term is dx to the 5th v against dx to the 5 plus 2 v. That came from the dx squared term. And then plus some lower derivative terms, and then plus these new terms, which are the delta dot of t terms. And these will be dx to the 5th v against dx v plus dx w bar.
It's delta. It's delta. Delta of t.
It's the speed.
Oh, delta. Sorry, this was the speed. Yeah, the phase shift. Yeah, delta dot was the speed of the shift, and that's the same one that's appearing in the equation. But what did I write? I wrote a sigma. What did I write? No, I want a delta. That's why. Sorry, wasn't a delta. Okay, so this is a good term. I integrate by parts. I get negative dx to the 6th v squared. That's the term that's going to control everything, plus some lower derivative terms. And then let's see what happens here. Well, this is a time derivative. It just came out. The x derivatives do not affect it. It's just a multiplier. And we have one term that is, did I do this right? No, this is going to be dx to the 5 plus 1. And this is dx to the 5 plus 1. Right. These two, these cancel. This is skew symmetry. So these cancel. This one's out. And then this one, well, this is just the right eigen function, dx. So it's really dx to the 5th of the right eigenfunction. I've just mentioned that that's in H5, it's bounded. So I can just bound this by Cauchy-Schwarz, and this one disappeared, and this one, so it's less than or equal to delta dot of t, and then dx to the 5th, or say v H5 times a constant, whatever the H5 norm is here. And then I remember, actually, this is order of VL2, VH1. If you remember, we actually estimated the size of delta dot and saw that it was little o of the L2 norm squared. Anyway, this is of the size of other lower order terms we've already neglected in previous arguments. We sweep all these together and we get less than or equal to negative theta tilde times dx to the 5th v. Sorry. I'm just going to put, H5 squared, and then plus a big constant times VL2 squared. That's our usual setup. And that's the estimate that one needs to prove. It's an exponential slaving of H5 to L2, and that gives, after an integrating factor argument, that gives a nonlinear damping estimate. It gives exactly this one.
Did you do on purpose H5 instead of H6?
Yeah, why did I? Yeah, I really meant to, because in these arguments, I'm always giving away one derivative. And that's because I'm not using the smoothing of parabolic operators, because that's not true for some other applications. I'm trying to do this in a way that every step of the argument also works for real physical viscosity, which is degenerate. It's not full rank, and even for hyperbolic systems, so relaxation systems. In that case, one gets no smoothing. So I don't want to use facts that are special to the parabolic equation. And that's why I'm doing it this way. But of course, how did I get rid of all these intermediate terms? There were some H5 terms in there, and but all of them I beat with Sobolev interpolation, which says I can take a small amount of H6 dx to the 6th norm, and I can control dx to the 5th by adding in a large multiple of L2. Yes.
So what's the X5 R? Why?
Oh, what R was the right eigenfunction. That's what I was calling it. And I just wanted to, that's dx, R is dx of W bar. So actually one of these derivatives just makes it into an eigenfunction. Otherwise, you know, it might look like something we don't know too much about, but yeah, we also know that this, from the traveling wave, the standing wave ODE, we know that this has exponential decay in many derivatives. So we could have just used that. But I'm also wanting just to emphasize that that's not, it's really just given to us by a theory with no information about the traveling wave at this point. Up to now, we didn't use any.
Just because of the previous theory of
The smoothing. Yeah. So it's a minor point, but I just want to keep everything in its box. And up to now, this is the ODE box. We did everything in a way that ignores the spatial structure. Okay, so this was the second point that this is where we didn't quite have time at the end of the last lecture. So now I've finished that. That was all we needed to finish the equivariance stability by the same argument. So we projected out the translational symmetry effectively, and this is a minor detail, but of course you need it. And it doesn't just, the thing is, we projected it out at the level of the linear estimates, and not and the nonlinear level. At least as far as I can see, we really need to do an energy estimate involving the whole equation, and I haven't projected out the shift, but it's harmless. Okay, so all right, so at this point, we have a nice coherent theory that could treat traveling wave stability in nice cases. And there are many nice cases. For example, stability of reaction diffusion. Usually it satisfies these conditions, but actually for shock waves, it's not satisfied. We're going to look closer, and but we're going to be using very similar techniques. Just we haven't looked very closely at anything. We'll look closely starting now. But the other point is, which is closely related, we haven't verified. We've shown that if certain spectral conditions are satisfied, then we have a nice nonlinear stability. But how would one verify those? And so that's the next step. We're going to talk about how to find the essential spectrum and the point spectrum. So good. All right, so get rid of this. Okay, I'll bring back my picture. I keep drawing, which looks like this. We have a shock. And this is like constant coefficient away from, we have a shock layer where the standing wave makes a fairly rapid transition, maybe not rapid, but it makes a transition. In there, it looks like a bounded domain problem, or heuristically, one expects that. So this should be point spectrum. And out here, constant coefficient, we think of continuous spectrum. So probably the essential spectrum has something to do with the constant state. So we'll do practice with the constant solution. Okay, linearize about a constant solution. Okay, so if we do this, and I'll do the scalar case. So we get VT plus A bar dxv equals dx squared v. And now this is constant. So that's much nicer. In particular, we can Fourier transform. So we get v hat dt equals, okay, negative I. I'm going to drop the bar. I a k minus k squared v hat. This is L. It's called L hat. It's just the Fourier symbol. Okay, so so we could solve this first of all, but I'm not interested in solving the equation. Right now, I just care about the resolvent. I'm looking for spectra. So lambda minus L hat inverse, or lambda minus L hat is lambda minus IA k minus k squared. That's the resolvent operator in Fourier transform. Now, I'm just going to look at the L2 spectrum. So that is where, and I'm just going to look for bounds from L2 to L2. I know I can lift those up to L2 to H2 if there's some resolvent point somewhere. So let's just look at this. Well, this is pretty easy. The inverse is just, this is all a scalar relation, a scalar expression. The inverse is 1 over this. And it exists and is bounded if and only if lambda is not in lambda of k, lambda of ik, which is iak minus negative iak minus k squared. So this is the dispersion relation, and whenever lambda is not in the image of the dispersion curve, we have a nice bounded resolvent. So that tells us exactly where is the spectrum. It's on the resolvent curves. And the same thing works for systems. We would just have A equals, without loss of generality, let's take it to be diagonal. And then because I chose such a simple viscosity matrix identity, which commutes with this, everything diagonalizes. And so we have lambda not, or lambda in the spectrum of negative I A J minus k minus k squared is the spectrum, which of L hat, which is the spectrum of L because of Parseval's identity. It's the same in the Fourier transform space as the original space. So what does this look like? Well, it looks, these are just parabolae. This moves us up at a certain rate, and the other one moves us out at a constant rate, and they are symmetric around the real axis. Okay, are these point spectra? No, because point spectra are isolated by definition. So this is the essential spectrum. And there's no point spectrum. Okay. that was our practice. And now that's quite suggestive. Oh, I'm sorry. A is A equals there you go. Oh, did I just erase it? A is equals df over dw of w bar, which is constant. It's the derivative of the Jacobian of the flux F in the original shockwave equation. Above, I took it to be scalar. Most of the time, I've taken it to be scalar, but it could, if it were a system, it would be a matrix. And I'm just looking at what I'm pointing out that at least when we have the identity as the viscosity matrix, it's actually, we can explicitly write down all the dispersion relations because it diagonalizes into scalars. Okay, so what if if A and the viscosity coefficient B don't commute? Well, it's harder, right? Because you won't be able to write it down explicitly anymore.
B, capital B.
Capital B would be, so what if I looked at dtw plus dx f of w equals dx b dx w, which is what a more general viscosity would look like. And so this could be variable coefficient, and it could be not commuting with the Jacobian of f. That's quite possible. Okay, so I won't say exactly what to do, but it's clearly harder. It's not explicit, and what you will do is, well, you'll look at small k and large k limits basically, and do some perturbation theory. Yeah, and so you can do enough, but that's a lot harder. I'm not trying to do the hardest things here. I'm just trying to show the method. Okay, but you can still work with that. Not much harm. Okay, so that was the practice. And now here comes a theorem. So this is the next goal. And you can find this theorem along with a lot of other theory in the book of Henry on parabolic PDE, properties, solutions of parabolic PDE. And I don't know if this is the first place this was stated, probably not, but here's the statement. It says, oh, sorry.
That's just it.
Right, no, so yeah, actually we don't have decay, right? If you write down the solution, and maybe that's another good example. So we have e to the minus ia k minus k squared t. If we take the matrix norm of that, well, this is just, this is imaginary, so that's modulus 1. This is e to the minus k squared t. Well, it's for k equals 0, that's 1. So it does not exponentially decay. In fact, it algebraically decays, as we're going to see. But, well, actually, from L2 to L2, it just doesn't decay. It, yeah, and not at a rate. It actually does decay to 0, but that's another theorem, and not at any known rate, not a uniform rate. Okay, so Henry's theorem says, okay, let L be a differential, a first order, well, not any, be a differential operator that with smooth exponentially converging coefficients or smooth coefficients exponentially converging at infinity. Okay, then the rightmost boundary of the essential spectrum of L is equal to the right envelope of the dispersion curves lambda equals lambda j plus or minus of ik at W minus and W plus. So around, in other words, the spectra of the constant solutions with the values of the end states. So matching this picture,
In case of which W is constant,
yes.
what's the analog of W?
It is translation invariant, but we don't have to worry about it because the derivative of a constant solution is zero. This one is actually, by luck, it's harmless.
Constant,
Oh, any other constant? Yes, but it's not within L2 of the original. So yeah, actually, good point. That's the real reason. Not what I said before. Is what? Yeah, you're right. Yeah, it's because other constants. So there are two kinds of shifts. There's the shift in space that we worried about before, and my answer eliminates that because the derivative of constant is zero, no harm. You can shift a constant and it's still constant. So that's not an issue. So that is within the symmetry class, those perturbations. The other question is, isn't there also a translation invariance kind of in the dependent variable? As you point out, I could have constant solutions at any value, but those are far away in L2. That's how we get out of that. Yeah, so moving to one of those would take us out of range. So that's, yeah. So actually all the theory that we gave, that would apply to this problem of the constant stability, except that we wouldn't get exponential decay. We would just get, and we wouldn't even get boundedness the way we did it. We would get a arbitrarily small exponential growth at the linear level, and we would get nothing at the nonlinear level. It's just not built to handle this. Okay, so yeah, here's the picture. I have to draw this picture again. I don't think it's very clear. Okay, so for the scalar case, we have one dispersion curve. Let's just call it lambda plus. I don't need a 1, 2, 3. There's only one. And then there's a lambda minus, which is the dispersion curve for the constant solution at minus infinity. So there are actually two of these. And what I mean by the right envelope, I mean toward the real side. The envelope is just, in this case, it's simple because these don't intersect. Let's see, it could be in more general cases where I allow the viscosity coefficient, the parabolic coefficient, to depend on space. It could be that these could cross, and then it would be more interesting. But you can have, I didn't say anything about the nature of this operator. So the dispersion curves could be quite wild. And you could have, so this is more generally, you could have something like, you could have anything, right? You could have something that looks like this, and then some other thing that looks like this. And the rightmost envelope would then be tracing along the farthest points to the right. And
identified with lambda plus?
Well, here it would just be, it actually depends on the particular values, but yeah, it could be that lambda minus lies to the right. It could be that lambda plus lies to the right. But in our case that was particularly simple, there will only be one that's to the most to the right. There will be no intersections except at 0. But that is a special case. I didn't assume away this kind of thing or worse, because in general there would be more than 2 spectral curves. Like for the system case, it could be quite wild, but it doesn't really matter. It's just a linear algebraic condition. It's in principle computable, or at least numerically estimable. For a large system, yeah, you can't explicitly solve, but you can quite nicely estimate these curves. And since, as I'm kind of suggesting, we really want them to be strictly negative in order to have strictly negative real part. That's something that can be validated by rigorous numerical proof. It's quite okay. So, okay, so this is pretty satisfactory as far as finding these. Okay, so the proof. Okay, we'll prove the first part. So I claim there are 2 parts here. I claim that all lambda in any of these dispersion curves are in the essential spectrum. Yeah, and that is, okay, that's because we know that let's lambda minus L. Okay, let's try plus infinity, just to fix things. So there's the constant coefficient operator. Constant coefficient limit, I'll call lambda plus. Yes. This is the variable coefficient. Yeah. So this is our first. Yeah, we haven't mentioned anything about how to find where it is, but now we say almost exactly where is the essential spectrum. So that's a big step.
The plus and minus are the operator at the limit of
Oh, these are the dispersion curves. So lambda j of ik. Lambda j is these are the in the constant coefficient case, they were the spectra of the symbol. Those are the lambda j of ik.
non-constant coefficient.
Yeah, but now it's in the non-constant coefficient case, I'm putting the plus or the minus to indicate that I do this analysis around the constant solution W plus, the plus limit, or with W minus.
So they are the limit at when x goes to plus infinity.
Yeah.
Of the operator.
Not, let's see, of the operator, yeah, I guess the operator as well. Yeah, that's true. But mainly it's just the end state. I'm just saying if I pretend like everything is constant, at plus is constant with the value W plus, that is the end state of the shock, right? This, maybe it's good to put the picture back for a second if I can find it. Oh, no, let's see. I might have erased that nice picture. I did. Okay, well.
We are assuming that L is the linearized operator
around the full shockwave. Yeah, but now I'm relating the essential spectrum of that complicated operator to the essential spectra of the limiting constant coefficient operators. So yeah, it's exact. I guess you said that. It's exactly that. That is another way of saying it. Yes. Yeah, sorry, I think I confused that.
That's the exponentially convergent. That's exactly the exponentially convergence coefficients.
Yes, right. Yeah. And so it's this, for our problem, it's the same ones that I just computed, these parabolae. So we know exactly where they are for the scalar shockwave problem. They're here. And but okay, the first claim is these are actually, they are essential spectra. And okay, and so so this is lambda minus I a k minus k squared, or lambda, so lambda of I k. Okay, this is set up to be 0 times okay, times some eigenvector, which in this case is just 1, and it's 0. But this means this is in the transform. This means that there is, if I write lambda of I k minus L plus applied to r hat e to the I k x, that is 0. It's the same statement. L plus is just negative a dx minus dx squared. And you see that when that hits e to the ikx, it just brings down, every derivative brings down a factor of ik, exactly as in, I mean, this is the Fourier transform deconstructed, I guess. So I have such a solution. So now I'll look at chi of x, r e to the ikx. This should just be an r. And I'll take chi supported on minus or m to plus infinity, m very large, and going from and 1 on 2m plus infinity, so that with all derivatives order of 1 over m, which is the cutoff function. And now when I apply lambda minus L to this, you see, my only problem is this would make it a point spectrum if this were in L2, but it's not in L2. It's periodic. So instead, we cut it off. Let's see. Oh, did I do this? No, on M2, sorry, 2M. Yeah, this is what I want. Not one. It's just supported. And all the derivatives are order of 1 over m. I just need to stretch it out enough that the derivatives can be small. And I want it to be, yeah, that's fine. That's all I need. Because now see what happens. Now I've made a wave packet out of it, and that is in L2. But if I take L, or lambda minus L, and let's call this Vm. This is the actual variable coefficient. Okay, that's equal to lambda minus L plus Vm plus L plus minus L minus Vm. And this is, okay, so this is lambda minus lambda minus L plus applied to chi times Vm plus chi L plus of V, not chi Vm, chi of R e to the ikx and lambda minus L plus, sorry. This is 0.
But what is lambda? L minus there? L plus?
This is L plus, and this is lambda minus L plus. Let's see. This is lambda minus L plus. This is L minus L plus. Oh, it should be the reverse. You're right. It should be L plus minus L to add up. I want it to add up to lambda minus L plus. Now it should.
Plus
Yeah.
one.
Let's see.
Plus minus
Oh, yes, there we go. Thank you. That's why. Yeah, now it works. And this one's exactly 0. And then this one is exponentially decaying. So that has a something small in front of Vm. This one is 0. And yes, and this is order of 1 over m because it's derivatives of chi. Okay, so we find that lambda minus L Vm goes to 0 as in d of, as it goes to 0 in x, but Vm does not go to 0 in d of L.
But m is fixed?
M is as m goes to infinity. Yeah. So we're going to now take m to infinity, and we have better and better approximations to an eigenfunction. And the pieces that we leave off, they're small and estimable. Those go to 0, but Vm itself does not go to 0 in norm. It's almost constant in norm.
Why is it?
Well, because it's I'm just let's see, am I doing that right? Is it almost constant in norm? Let's see. No, it's of the order of m, right? It's m times a constant, roughly, because I'm increasing the number of periods that I allow, basically, because I go from m to 2m. But the ratio of Vm to these error terms is still small. I mean, I have the same periodic extension going on both sides. But these have an exponential decay in front of them, and these have a 1 over m in front of them. So the ratio of image to pre-image is still going to 0. And that means that this has not got a bounded inverse. So it is essential spectrum by the definition. So you could just do it by definition. All right, and I've gone over. I apologize for that. The next part will be in the following lecture, and for that I need to do some ODE theory to actually see what's going on. Yeah. So what I want to show next is, so I've shown that these are essential spectra, and therefore the rightmost boundary is at least to the right of this curve. Now I want to show there's no essential spectrum to the right of this curve. That's the next part, that all this could only be resolvent set or point spectra. And for that, I need to learn something finally about the resolvent and what it looks like. But we're going to learn a lot more than we need for this. Basically, we're going to get a very complete description of the resolvent next time. We're going to do basically we're going to reduce to constant coefficients again, in a way. But as this all suggests, but there are two constants. So we're going to reduce to a pair of constant coefficient equations and some kind of condition. And Okay, that's also similar to what Henry does in his book, but he has a very different proof, but it comes down to the same comparison. So we stop there. This is actually where I anticipated stopping. Okay, so any questions from either spot? Okay.
I guess I'll ask one if that's okay.
Yeah.
Yeah, so is this theory in any shape or form related to this limit absorption principle by Agumon?
Oh, that's I would say what I'm going to be showing in the next lecture, which is a bit different, does very much have a connection to that. But this, I don't, as I understand the absorption principle, I don't think this has, no, I don't think it does.
Yeah, it looks a little bit like it because like for the limit absorption principle, the idea is also that your when your resolvent operator acts on something, that thing goes to zero, but then the thing itself escapes.
Mhm. Well, let's see. I'm going to suggest, okay, let's wait for next Tuesday, and when I give you the I'll show you the step B. That's the one that would be related. I don't think it quite is, but things that I do immediately after, I think they are.
Sure,
So I'll ask you if you think it'll be a little more concrete and we can discuss it better.
sure. Thank you.
Okay,
Thank you.
that's I like that question though. Good. Okay, good. Thanks. Thanks for your patience. Didn't realize I was going over. Okay. Any more questions out there? Okay. All right. I'll see you on Tuesday, and a few of you I'll see sooner. So take care.